8 years. That's how long it takes the average electric car battery to lose enough capacity that owners start noticing it on the dashboard. Not failing, not dying, just quietly getting worse every single month, the way a phone battery does. Except the phone costs you $80 to replace and the car costs you $14,000. Now forget that number, because a battery just rolled off a production line in eastern China that isn't supposed to do that at all. Not degrades slower, not lasts longer than expected. The engineers who built it are making a claim that would have gotten them laughed out of any battery conference 5 years ago. Under normal use, this cell is expected to retain effectively all of its original capacity for the entire working life of the vehicle it's installed in. And it's not a lab sample sitting under glass at a trade show. It's already been welded into the floor of production cars driving on real roads right now. If that sounds like marketing language dressed up as a headline, stay with me, because the chemistry behind it is real. It's been public for over a decade, and the only reason you haven't heard about it until this year is that nobody could figure out how to manufacture it at a price that made sense. Until now. By the end of this video, you'll understand exactly what changed, why the entire battery industry built itself around a compromise everyone knew was temporary, and why the next 18 months are going to decide who controls the next 50 years of how the world stores energy. If you're into stories like this, hit like and subscribe now so you don't miss where this goes, because what happens after this technology scales is a much bigger story than the battery itself. To understand why never degrades is such an enormous claim, you have to understand what's actually happening inside a battery every time you charge it, because it's not what most people picture. A lithium-ion battery works by shuttling charged lithium particles back and forth between two electrodes through a liquid, called the electrolyte. Charge the battery, and the particles move one way. Use the battery, and they move back. On paper, that's a clean, reversible process that should, in theory, run forever. In practice, it doesn't, and the reason is almost mechanical rather than chemical. Every single time those particles move through the liquid, a small number of them don't make the return trip cleanly. Some get trapped in microscopic structures that form on the electrode surface, a kind of chemical scar tissue the industry calls the solid electrolyte interface. Some of the liquid itself slowly breaks down from repeated exposure to voltage and heat, turning into gas or sludge that no longer carries charge. Some of the physical structure of the electrode itself expands and contracts with every cycle, the way flexing a paperclip back and forth eventually snaps it, until the material literally cracks at a microscopic level. None of this is a manufacturing defect. It's not something that happens because a factory cut corners. It is the unavoidable byproduct of using a liquid to carry charged particles between two solid surfaces that are constantly expanding, contracting, heating, and cooling. Every full charge cycle leaves the battery microscopically worse than the one before it, and those tiny losses compound. This is why every EV manufacturer on Earth quotes battery degradation in a range instead of a number. 10 to 20% capacity loss over 8 years, or 100,000 miles, whichever comes first, is considered a good outcome in the current generation of packs. Some vehicles do noticeably worse, especially in extreme climates. A handful do a little better with careful thermal management. But the trend line only ever points one direction, and every engineer in the industry has understood exactly why since roughly the 1990s. The honest answer to why hasn't this been fixed is the same answer you'll hear in nearly every industry that gets disrupted eventually. The compromise worked well enough for long enough that fixing it properly never became urgent until someone else made it urgent by fixing it first. Here's what that degradation actually looks like when it lands on a real person instead of a spec sheet. In 2023, A wave of second-hand EV listings in Norway, one of the most EV-saturated markets on the planet, started showing something dealerships hadn't planned for. Buyers were requesting battery health reports before they'd even sit in the car, the way you'd request a compression test on a used engine from the 1990s. Cars with genuinely low mileage were getting priced down by thousands of dollars purely because their battery reports showed capacity loss above what the algorithm expected for the miles driven. The car ran fine. It drove fine, but a number on a diagnostic screen had already decided what it was worth. That's the part traditional car buyers never had to think about. A gasoline engine with 40,000 miles on it doesn't have an invisible meter counting down its maximum possible range every single time you start it. An EV battery does, and that meter only moves in one direction. Insurance companies noticed the same pattern from a different angle. Total loss thresholds on EVs kept getting triggered by damage that would have been a simple repair on a combustion car, because replacing a degraded or damaged battery pack costs so much relative to the vehicle's remaining value that insurers do the math and total the car instead. In parts of the used EV market, this created something close to a standing joke among mechanics. The battery is worth more than the car it's sitting in, right up until the moment it isn't worth anything at all. None of this made electric vehicles bad products. Millions of them have performed exactly as promised. But it created a specific, quiet form of anxiety that gasoline car owners never had to carry. The sense that the most expensive single component in your vehicle is aging on a clock you can't see and can't stop. And that clock is ticking every time you plug in. That anxiety is the actual market this new battery chemistry is aimed at solving. Not top speed, not charging time. The thing that made an entire generation of buyers hesitate at the dealership. The fix, in theory, has been sitting in research papers since the early 2010s, and the concept is almost embarrassingly simple to describe, even though building it took over a decade. Instead of moving lithium particles through a liquid, move them through a solid. That's the entire idea behind what's called a solid-state battery. Replace the liquid electrolyte with a thin layer of solid material, usually a ceramic or a sulfide-based compound that still allows charged particles to pass through but doesn't degrade, doesn't evaporate, doesn't catch fire, and critically, doesn't leave behind the microscopic scar tissue that eats away at capacity cycle after cycle. Remove the liquid, and you remove almost every mechanism responsible for long-term degradation in one move. There's no solvent to break down under heat. There's less physical swelling because solid-state designs allow for electrode materials like pure lithium metal anodes that were considered too unstable to use safely in a liquid system. And because there's no flammable liquid inside the cell at all, the fire risk that has plagued lithium batteries since the earliest recalls essentially disappears. Along with the heavy cooling and containment hardware every current EV pack needs to carry as a safety margin. On paper, it solves three problems that gasoline-era engineers considered permanent features of electric vehicles: degradation, fire risk, and weight. Solving all three at once is the kind of claim that gets researchers funding. Building it at automotive scale, cheaply enough to put in a car a normal person can afford, is the part that stayed theoretical for 15 years. The reason is manufacturing, not chemistry. A solid electrolyte has to maintain perfect, gapless contact with both electrodes across an area the size of a dinner plate, repeated across hundreds of layers inside a single battery pack, without a single microscopic void anywhere in that contact surface. A liquid electrolyte does this automatically, because liquid flows into every gap by definition. A solid does not. Getting a rigid material to maintain flawless surface contact with another rigid material, at a scale of millions of units a year, at a cost that competes with a technology that's had 30 years of manufacturing refinement, is one of the hardest unsolved problems in industrial chemistry. That's the wall nearly every major battery manufacturer on the planet has been quietly running into since roughly 2015. While most headlines about the electric vehicle race focused on charging speed and range numbers, a much quieter race was happening inside battery research labs, and China treated it as a national priority years before most competitors took it seriously. Chinese battery manufacturers didn't invent solid-state chemistry. Japanese and South Korean firms held some of the earliest and most important patents in the space, dating back to the 2000s. But patents and mass production are two entirely different games, and mass production is the game China has spent the last decade systematically winning across nearly every battery chemistry it has touched, from the lithium iron phosphate cells that now dominate the global EV market to the sodium-ion cells that started shipping in volume over the past 2 years. Starting around 2021, Chinese battery makers began pouring capital into solving the manufacturing problem specifically, not the chemistry problem. Government-backed research consortiums brought together material scientists, equipment manufacturers, and automakers under the same roof, with an explicit target: get solid-state or near-solid-state batteries into production vehicles before the end of the decade. Provincial governments offered land, tax breaks, and direct subsidies to any manufacturer willing to build pilot production lines. The same playbook that turned China into the dominant force in solar panel manufacturing a decade earlier. The approach that actually cracked the manufacturing problem wasn't a single dramatic breakthrough. It was closer to industrial persistence. Engineers found that instead of jumping straight to a fully solid electrolyte, they could first mass-produce a semi-solid, or hybrid, version, using a thick, gel-like electrolyte that behaves mostly like a solid but retains just enough flexibility to solve the contact problem that had stalled fully solid designs for years. It's a compromise, but a strategic one. It delivers most of the degradation and safety benefits of true solid-state batteries, while being manufacturable on production lines that don't need to be built from scratch. That hybrid step is what turned a 15-year research project into a product with a delivery date. Here's where the timeline stops being theoretical. Semi-solid-state battery packs began shipping in limited numbers in Chinese market vehicles starting in 2022 and 2023, initially in premium electric sedans, where the higher manufacturing cost could be absorbed into the price of the car. Early adopters reported something that made battery engineers outside China nervous: real-world range figures holding up far closer to their rated capacity after extended use than equivalent liquid electrolyte packs from the same period, along with battery warranties extended well beyond what any manufacturer had previously been willing to guarantee. By 2024 and into 2025, the manufacturing cost curve started doing what manufacturing cost curves in China tend to do once a technology clears the pilot stage. It fell fast. Production lines that had cost enormous sums to build as prototypes got duplicated, refined, and scaled, the same pattern that took solar panels from a luxury installation to the cheapest form of new electricity generation on Earth within about a decade. Battery manufacturers that had been quietly running pilot lines announced gigawatt-scale expansion plans, with public targets to have next-generation cells, including fully solid-state versions, in mainstream-priced vehicles before 2027. The claim that these batteries never degrade needs one honest caveat, because no engineer would sign off on the word never without an asterisk. What manufacturers are actually certifying is capacity retention above roughly 90% after the equivalent of a full decade of daily driving, under standardized testing that pushes cells through thousands of charge cycles under both extreme heat and extreme cold. That's not literally zero degradation across the laws of physics. Its degradation so far below what current EV buyers have come to expect, that functionally, for the ownership life of a normal car, it behaves like a battery that doesn't wear out. For a customer used to watching range estimates shrink year over year, the practical difference between never degrades and degrades imperceptibly slowly is not a difference most people will ever notice. That's already enough to change the calculation. Vehicles carrying these packs are being marketed not just on range or charging speed, but on something the industry has never been able to promise before: a battery warranty that quietly assumes the pack will outlast the car around it. Step back from the battery itself for a second, because the more important story here isn't really about chemistry. It's about what happens when the most expensive, most anxiety-inducing part of a $15,000 decision stops being a liability. Battery degradation wasn't just a technical inconvenience. It was a psychological tax on every electric vehicle purchase, one that showed up in resale values, insurance premiums, and the quiet hesitation of buyers who'd read one too many horror story about a used EV needing a battery replacement that cost more than the car was worth. Solve that problem convincingly, and you don't just improve a product. You remove the single biggest reason a cautious buyer chooses gasoline one more time. That's the scale of what's actually at stake in a manufacturing race most people outside the battery industry have never heard of. Whoever gets durable, long-life battery chemistry to automotive scale first doesn't just sell better batteries. They reset what normal means for an entire global industry. The same way lithium-ion itself reset what normal meant for portable electronics 30 years ago, and the same way solar panel manufacturing shifted the center of gravity for an entire energy sector a decade later. Western and Japanese manufacturers are not standing still. Several have their own solid-state programs, some with impressive lab results and ambitious announced timelines. But timelines and manufacturing scale are different things, and the gap between a battery that works in a lab and a battery that ships in 1 million cars a year has historically been where Chinese manufacturing has closed distances that looked insurmountable a few years earlier. Battery chemistry decisions made in the next few years won't just decide which car company wins a sales quarter. They'll decide which countries' factories, supply chains, and manufacturing standards become the default the rest of the world builds around for the next several decades. The same way today's global lithium supply chain was locked in by decisions made back when lithium first won its own race for dominance. Whoever's factories are already scaled when the rest of the industry catches up doesn't just have a head start, they have the blueprint everyone else has to license, copy, or compete against from behind. The battery that never seems to wear out isn't the end of this story. It's the opening move. So here's the honest way to think about where this leaves things. The chemistry that could finally kill EV battery anxiety isn't science fiction anymore. It's been engineered, scaled, and welded into cars people are driving on real roads today. The question left standing isn't whether this technology works. It's who controls it at scale when every automaker on Earth eventually needs it, and what that does to a global auto industry that spent the last decade rebuilding itself around a battery chemistry that just became yesterday's compromise. If this changed how you think about the battery sitting under the car in your driveway, hit that like button and subscribe so you don't miss what comes next. Turn on notifications, because we cover stories like this every week. Now I want to hear from you in the comments. If a battery that barely degrades became standard within the next 5 years, would that finally be the thing that gets you into an EV? Or is range and charging speed still the bigger hesitation for you? Let me know below. And if you thought the battery was the whole story, wait until you see what's happening to the mines that supply the material this technology was built to replace. That's next.